Hi, I'm Randall Heyman, a mathematics academic. Because of the coronavirus outbreak, I'm making quick turnaround videos for educators and their students. If you'd like more information about what I'm trying to do and about me, have a look at here. Have a look at this, the first video in this playlist. If you'd like to send me an email so I can do a problem for you or your students, there's my email address, or you can leave a comment under the videos that I'm making. So this is part 2 of metric spaces for Lydia. And here I want to give some examples of some metric spaces. So let's go example 1. I'll do 3. This one's called the taxi cab metric. So let's have here a point x1, y1, and here we have the point x2, y2. And the normal metric goes along this line here. I'm just going to do it in, let's do it in light blue. I think I've got it on, yep, I've got it on fine. Imagine that's straight. So that's what we're used to. I suppose the shortest distance between the two. So here, what we envisage is we go across here. It's like a taxi has to follow the road, and then it goes up here. All of these are straight lines. So the other way the taxi cab could go is, let's do it in red, could of course go up this way and across this way, which will give the same result. But anyway, let's just think about this. So here we've got the Cartesian plane. So this is x1 and this is x2. So this point here would be the point x2, y1. Okay, so the distance function here between point x and y is given by the absolute value. Firstly, this bit here, this is 1, and then we'll do 2. So if we look at 1, what's the distance between this? Well, you could use the distance formula that I had in the previous one, the square root of the sum of the squares of the differences of the x and the y's. But here you can just see that y doesn't change. So going across here, we're just going from y1 to from x1 to x2, and the y's don't change. So it's just the difference between x2 and x1. And you can see I've used the absolute value symbols here because we can't have a negative in terms of the distance for this metric space that we're creating. And then we'll just do, when we go to 2 up here, when we go to 2, we're just going from y2 to y1. x2 is the same, so we'll just go y2 minus y1. So that's our distance function. So the metric space, I suppose, would be R2 with the row function that I've explained here. That would be the metric space. Okay, so that's one. Now with any of these, you might like to actually try and prove that it satisfies all the definitions that I had in the previous video. That's a very good exercise. I'll probably do one of them in the next video. Okay, now the next one is the discrete metric. And this is a binary type on-off sort of situation, so it may be well suited to computer science type applications. So here we'll consider a point x, and we'll consider a point y. And here the distance between x and y is actually given by this. It equals 1 if x does not equal y, and equals 0 if x does equal y. Very simple, very simple. Very simple idea. Okay, so that's our second example. And the third example, I just want to show you that it doesn't necessarily have to, applied to points. So here, here we're going to consider the space of C01, which is, pardon me, these are all the continuous functions, continuous functions on the interval 0, 1. And here it's implied that when we talk functions, we're talking about the functions being the normal sort of, f is a function from R to R. Example, fx equals x squared. Now that is, this one here, this function here is a continuous function on the interval between 0 and 1. If we draw the function, there's 1, there's x, there's y, and it is continuous between 0 and 1, inclusive. So this function f here that I'm talking, I've given an example, this would be an element of C01. So I could just write that if you like, f is an element of, of C01. So first takeaway from this example is that you don't need a metric space to involve points on R1 or R2 or R3 or anything like that. Okay, now what's the metric? Well, the metric between, say, f and g, which are two functions, is the maximum of the set of the distance between fx and gx, where x is an element of 0, 1. So what is this saying? What is this saying? This is saying it's just the maximum difference between f and g on that interval 0 to 1. So let me just draw a little diagram. Here we've got x, y. Let's call this 1. This is x, this is y. Okay, I'll draw, this is f, x, and now I'll draw g. I've got to draw it so it's obvious what's going on here. Okay, and now we look for where's the maximum difference here between the two functions. Actually, let me go back and just label that g of x. And let's just draw a dotted line here. So we take the green pen and we just look at all these distances and we just say, where's the maximum distance? And I think, see, this was a bad example. I picked a bad example. I suspect that's the maximum distance between them. Maybe it's there. But anyway, that will give you an insight into how that one works. So hopefully those three examples have given you a sense of the scope of, or how wide or how much this idea of metric spaces can be generalized. Actually, just before I go, sometimes you'll see here instead of max, they'll write the word sup, which is short for supremum. I don't think you need it in this case because we're talking continuous functions, but sometimes you'll see in this definition of this the word sup. Okay, that's all I wanted to say about this. In the next video, I'll do a proof that a metric space or a distance function actually is a proper, satisfies the definition. And if you've got any questions on metric spaces or anything else in mathematics, please drop me an email or comment below the video.